right, we've moved on. We're now talking about equilibrium. So the last chapter dealt with chemical kinetics. Equilibrium now is just you've already reached equilibrium. Kinetics is the only chapter you have to deal with how fast things are going. Now we've got to equilibrium, and this is gonna dominate for the rest of the rest of the semester up until we get to nuclear chemistry. So really, equilibrium is an important concept. So the idea of equilibrium is that the forward rate equals the reverse rate. We use this sometimes colloquially. Equilibrium also means balance. Like if you get hit in the head and you lose equilibrium, you have a hard time balancing. And balancing actually takes a lot of work. If you ever sprained an ankle, you know how hard it is to walk and keep your balance. So it's actually a lot of work and just standing still. You're standing still. You're teaming with activity. Still a joke, what are you doing? Like, well, looks like I'm doing nothing, but on a molecular level, I'm teaming with activity. Yes, that is the essence of equilibrium. Even though it looks like nothing is going on, lots and lots of activity is taking place. So here's a couple examples. So hemoglobin, although it's more complicated than this, hemoglobin actually can take on four oxygens. But the textbook goes over this with the hemoglobin, the fetal oxygen. The idea is that the fetal oxygen is slightly more can hold on to oxygen a little bit better than non-fetal, and then it shifts that equilibrium, and more oxygen gets absorbed to the baby in the mother's womb. So there's other thing reactions that are reversible, and you can notice I denote this with this double arrow. So carbon dioxide plus water makes carbonic acid. So that's something that goes on in our bodies as well. So carbon dioxide that's burned, it's formed in our cells' mitochondria, dissolves in the cytoplasm of the cell, and ultimately can transport out of the cell into the bloodstream, and then to our lungs, and then exhaling it, we can release the carbon dioxide, and that's nice. And carbon dioxide, our body also uses it as a buffer. We'll talk about that in a subsequent chapter. And also just something else like hydrogen and iodine, making two hydrogen iodides. So here's another example of a reversible chemical reaction. And here you can see that you have the y-axis is concentration, the x-axis is time, and you start off with hydrogen iodine, and as just reactants, as the reaction progresses, you get to a point where the concentrations don't change, and that's an equilibrium. It's dynamic because the forward and the reverse reaction are happening at the same time, but it's the concentration doesn't change. It's kind of like this. Another one, if you have an analogy here for immigration. So if you have a bunch of people in country A and you restrict the immigration in a country B, suddenly if you open it up and allow open immigration, the populations will be about even over time. Not to say that people won't be moving back and forth, maybe find a job on one side or fall in love and move to the other side, but then the emigration would be equal on both sides, and then there'll be no net change in population for either countries. So let's talk general. Here is the most general chemical equation you ever have. Little a of big A species plus little b of big B. So the small lowercase ones are the coefficients, the stoichiometric ratios. Forms little c of big C product and little d of big D product. And the K, the equilibrium constant, so there's an equilibrium constant. The constant does not change because the concentrations don't change. These are the concentrations of the products raise their coefficients. Oh, the concentration of the reactants raise their coefficients. And those concentrations are all at equilibrium. And I always remember it's products over reactants. And remember those brackets means moles per liter. So these are pretty easy. Express the equilibrium constant for this following reaction. Methanol breaking apart into synthesis gas, carbon monoxide and two hydrogens. So it's products over reactants, carbon monoxide, hydrogen squared because of the 2 in front of it, over the reactants, methanol. That is the equilibrium constant. And what does this equilibrium constant tell us? So if K is really small, that means that the reaction does not proceed very far. So, for instance, nitrogen plus oxygen forming 2NO. There's nitrogen and oxygen in the air right now. Why aren't we forming a bunch of NO? Well, we are forming NO, but the number is just really small, and because of that, we don't really see that much nitrogen monoxide in the air at this temperature and pressure. If K is about 1, that means that the reaction goes about halfway. Truth be told, if it's somewhere between, say, 1,000 and 1,000th, you will see you will experience both reactants and products in reasonable amounts. And why is this important if you have reactants and products in reasonable amounts? Like, well, because then they're there, and then they can react with other things. So if you're working on some industrial process or something, and it turns out that one of these materials can react with your container or can form a bad byproduct, or if you're out in the open and one of these is poisonous to biological creatures, that can be a bad thing. So that's one thing about equilibrium constants. Then between like 1,000 and 1,000th, that you will see all species in the chemical reaction. If K is huge, that means that the reaction is favor the forward reactor, which goes all the way pretty much to completion. So if K is big, so what does it mean if K is big? That means that the products are big and the reactants are small. And reactants are called the left and products are called the rights, because the product's on the right side of the equation. So for K being huge means you have a big number over a small number, which means products are big and reactants are small. And if K is small, that means you've got a small number over a big number. You have little products over a huge amount of reactants. So for me, myself, I don't even memorize this. I just I just logically think it out every time. If you want an example of a product reaction that goes very far, it's hydrogen plus bromine makes hydrogen bromide. That is very far to the right. Okay, what do you think about this? If so, at a certain temperature, the equilibrium constant of ammonia synthesis is 0.95. The reaction this way would go halfway. Let's talk about relationships with the equilibrium constant. If you reverse the equation, you invert the equilibrium constant, right? So let me make it simple. A in equilibrium with B, the equilibrium constant is product over reactant. If you invert it, that means that the equilibrium constant is also inverted. If you multiply an equation by some factor, you raise the equilibrium constant to that factor. So you can see here, if you have the same A in equilibrium with B, if you have N of A over N of B, the new equilibrium constant is the older equilibrium constant raised to that power. And for a multiple step reaction, use your overall reaction for the equilibrium constants. Like if you have some intermediate that is generated and destroyed, you can just leave it out of the equilibrium expression altogether. Okay, so let's look at this. What is the equilibrium constant so the equilibrium constant for the ammonia synthesis at this temperature at 25 degrees Celsius is 3.7 times 10 to the 8. What is the equilibrium constant for ammonia? And why would you do this? To program Excel documents. So if you want to, we chemists, we use Excel like everyone else does, and you program the cells to do things. And so this one you could program it for ammonia. So okay, what are you doing? You're inverting the equation, right? So you have ammonia on the left and nitrogen and hydrogen on the right, and also you're divided by 2. So right, you're inverting it and you're divided by 2. Divided by 2 is the same thing as multiplying by a half. So our new equilibrium constant is going to be 1 over the old one raised to the 1/2 power, which is 1 over the square root of K, which is 1 over the square root of 3.7 times 10 to the 8th. And that is I guess I need to use my calculator for this one. I was thinking I could do it in my head. Sorry. Where is my calculator? All right. Sorry for the slowdown here. 1 divided by the square root of 3.7 exponent 8. And this is 5, how many sig figs? 5.2 times 10 when you count the zeros. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, 6. Times 10 to minus 6. Oh, wait, is that? Yeah, that's right. 1, 2, 3, 4, 5, 6. Yep. Okay. So let me, out of curiosity, let me square that. And let me invert that. Answer. Yeah, that's right. Okay. Wait. Yep. All right. And all right, next thing, let's talk about gases. So let's look at the example here. 2 SO3 gas in equilibrium with 2 SO2 and oxygen. So on the left, there are 2 moles of gas. On the right, there are 3 moles of gas. So I'm just counting up the so SO2s, there's 2 of them. I'm sorry, it's SO3s on the left. There's 2 SO3s, there's 2 of them. On the right, there's 2 SO2s plus 1 O2, that's 3. Those are the moles of gas on both sides of the equation. So there's the Kc is the concentrations, but since concentration is directly proportional to pressure, we can just put the pressures. It's much easier to use pressures with gases. But the Kc and the Kp are related by the Kp equals Kc times RT raised to the delta N power. And the delta N is the change in the number of moles of gas, is always final minus initial. So in this case, the delta N is plus 1. So let's relate this. So looking at this one here, so we have 2 NOs plus O2 goes to 2 NO2. So, and our Kp is 2.2 times 10 to the 12th. So we want the Kc. So find the Kc. So the Kp equals Kc over RT to the delta N. That means Kc is going to be Kp over RT to the delta N power. I should say, oh wait, I'll put the parentheses in the wrong place. RT to the delta N power. Okay, so that means this is 2.2 times 10 to the 12th all over R. So 0.08206 liter atmosphere over mole Kelvin. Temperature 298 Kelvin. And the delta N, it's N final minus N initial. And there are 2 moles minus 3 equals minus 1. So this is all raised to the minus 1. And you put that into your calculator and you get 5.4 times 10 to the 13. 5.4 times 10 to the 13 is what you have there. So that's your answer there. All right, so try this one out if you will. Give it a go. And what's so nice about this, the delta N is 0, so the Kp equals the Kc. All right, so next concept, let's talk about reactions that involve liquids and solids. So question, what is the concentration of water, of liquid water? The answer is it's 55.6 molar. So it's there's 100 grams in 1 liter of water. I'm sorry, 1,000 grams in a liter of water. So 1,000 divided by 18. So that's 55.6 molar. So liquid water is 55.6 molar. That's so that's pure water. And does that change if you have a drop of water or if you have an ocean of water? I know oceans are salt water, but let's say something okay like Lake Tahoe in California, some huge body of fresh water. So, is there a difference between a raindrop, a beaker, and Lake Tahoe, all assuming the same pure water? The answer is no. Always has the same concentration. Liquids and solids have a constant concentration. So, whenever you deal with this, you get rid of them. So, this is two carbon monoxide gas in equilibrium with carbon dioxide gas plus solid carbon. So that's carbon solid. So solid carbon and products over reactants. Carbon is a solid, so you remove that and you just write the equilibrium constant that way with the expression of the concentration of carbon dioxide, concentration of carbon monoxide squared. So the next thing we're going to talk about, you will do over and over again. So you will see this quite a bit. And this is doing what's called the ICE chart, initial change equilibrium. So pay attention here because you will go over this quite a bit several times. For the next two chapters, you will use this concept. Well, the rest of this chapter, and then the acid base and buffers chapter. So consider this equation: carbon monoxide plus 2 hydrogens makes methanol. So the initial concentration has carbon monoxide being half molar. So I'm going to put there 0.5. Hydrogen being 1 molar. At equilibrium, carbon monoxide concentration is found to be 0.15 molar. What is the value of the equilibrium constant? So equilibrium, this is 0.15. Now, the idea here, and what can we infer? So I'm going to infer in pink. I'm changing colors for those of you who can't see the colors, but since it says initially half molar carbon monoxide, 1 molar hydrogen, that means we have a 0 there. So that means that since it's not listed, it's 0. And if it goes to 0 to 0.15, that means that this adds 0.15. So if I'm highlighting methanol, if methanol increases by 0.15, that means that our extent of reaction. So what we can infer from this is that carbon monoxide, if methanol is gained by 0.15, methanol will decrease by 0.15. Also, hydrogen will decrease by 0.3. And by 0.3. The reason for this is because there's a 2 in front of hydrogen. So this is also called the extent of reaction. So the extent of reaction for this reaction is 0.15. That means this reaction goes forward at a rate of 0.15, at least to completion. So that means that carbon monoxide, we will lose 0.15 reactants. Hydrogen, we will lose 2 times the extent of reaction, or 0.3. And then methanol, we gain 0.15. And then we can calculate this down. So you just take these lines and you add them together. So 0.5 minus 0.15, this is 0.35. And 0.1 minus 0.3, this is 0.7. I shouldn't be consistent. I'll say that. I still get that little tail on my 5. There we go. Less of a tail. There we go. All right, so again, these numbers come from, so the blue that I put in first, the initial is 0.5 for carbon monoxide and 1 for hydrogen. And also it was given to us that the equilibrium concentration of methanol, CH3OH, is 0.15. Those are given information. We can infer that there's no methanol, and then from the fact that methanol went from 0 to 0.15, that we gained 0.15. And that is, since the extent of reaction is 0.15, that means we're going to lose 0.15 of carbon monoxide, and 2 times 0.15 or 0.3 for hydrogen, because there's a 2 in front of hydrogen. And then If we start with 0.5 and we lose 0.15, that means that we have 0.35 molar carbon monoxide at equilibrium. We have 1 minus 0.3 or 0.7 molar hydrogen at equilibrium, and already established 0.15 molar methanol at equilibrium. Now, the equilibrium constant, it's going to be products over reactants raised to their power, so that's methanol over carbon monoxide hydrogen. Now we just put in the numbers. I'll go back to blue. I like blue. So put in the numbers as 0.15 divided by 0.35 times 0.7 squared, and you put that in your calculator, and you get 26. And that is the answer. So answer right there. And also I told you that when a K is close to 1, that you see, I said somewhere between 1,000, 1,000th, you'll see both reactants and products there. This is an example of that. You're going to see, in this reaction, you see both products and reactants in fairly reasonably close amounts, right? So, okay. And keep this ice chart in mind, though, because we're going to use this for the rest of the chapter and the subsequent chapters.